Welcome to Data Management with Python and SQLAlchemy. My name is Christopher, and I will be your guide. This course is all about interacting with databases in Python through the third-party library SQLAlchemy. In this course, you'll learn about SQL, also known as SQL, the language used to interact with most relational databases, and then dive into SQLAlchemy, a library for using SQL concepts in Python. SQLAlchemy breaks down into two parts: core, which allows you to write SQL statements directly or use functions to do the same, and the second part, the ORM, an object relational mapping implementation that lets you treat rows in a database as objects. The code in this course was tested with Python 3.12, SQLAlchemy 2.0.23, and SQLite 3.37. Note that there have been major changes in SQLAlchemy since the previous 1.4 and even more changes from the previous 1.0 version. If you aren't using 2.0, you are going to run into problems with the examples in this course. What is software besides a set of rules for manipulating data? And oftentimes, you want that data to persist between execution of your program or to be passed between programs. You may have used a text file, also known as a flat file data representation, for storing data. These can be useful, but often have limitations. A database provides a more robust way of representing data objects and their interrelations. There are actually different kinds of databases, but the most common is what is called a relational database. If someone just says database to you, they probably mean the relational kind. Most relational databases support the structured query language, or a dialect of it, for managing the contents of that database. SQLite is a popular, self-contained, single-file database engine. One of the beauties of it, especially if you're just learning databases, is that it doesn't require a server. It has all the power of a database, except it's local to your file system. And seeing as you're here at Real Python, the question probably is, great, but how do I use it with Python? Yep, well, there are actually many libraries that can help you interact with databases. I'll be covering SQLAlchemy, a third-party library with several different styles of interaction. Next up, I'll introduce you to data storage through the use of CSV files. Gotta walk before you can run. In the previous lesson, I gave an overview of the course. In this lesson, I'll talk about CSV files as an example of flat file storage. Your software stores data in memory through the use of variables, but like life, this is fleeting. Exit the program or turn off your computer, and the memory is gone. This can be addressed through saving things out to some sort of storage, usually your disk drive. A side benefit of this is, if it's done well, it can be used to interact with more data than can be held in memory at any one time. Flat file storage is a generic term for text-based files that typically can be read by a person. There are many different formats. Some common ones are CSV, the one which I'll be using shortly, JSON, and the granddaddy of angle brackets, XML. Let's go look at a program that uses Python's CSV module to see the kinds of things that can be done with a flat file format. And here it is, 14 lines of data. This is a listing of books. CSV stands for comma-separated values. And looking at this data, you can probably see where it gets its name. It's a list of values separated by commas. Clever, huh? A lot of CSV files have a header line by convention. The header line gives the name of each column of data. I've highlighted it here. After the header row, each row here is a book with the author's first and last names, followed by the book's title and then the name of the publisher. In the case of special characters, for example, wanting to have a comma, you typically surround the value in quotes. CSV is a loosely defined thing. You will run into variations on how to use it. But the format here is what Excel uses, and being one of the most popular programs on the planet, weighs pretty heavily. Here is some code that reads in that same CSV file and prints out some summary information. It does this through the use of the CSV module, in particular, the dict reader class. The dict reader takes a file which it expects to have a header row and then allows you to iterate over that using a reader. The reader will contain a series of dictionaries. The keys in each dictionary are the column header name, while the value is the corresponding value from the row. I'm using a default dict here to store some summary information. The default dict is created with an integer, which means you can assume that a key exists, and if it didn't, the default dict will create one automatically for you in the form of an int. I loop through each row of data, adding the author's name and publisher's name into the respective dictionaries to form a count of occurrences. After that, I print out a summary of how many instances of each author name and of each publisher. Let's go run this. There you go, a count for each author and a count for each publisher. CSV has some limitations. For example, data is repeated. There are 4 books by Stephen King and each get a row. That means Stephen's name shows up 4 separate times. This is because everything is from the row's perspective, which in this case is the book. If I want to add the age of an author, technically I can do it, but I'd have to store it on each of the 4 instances of King's books. If I need to make a change, I'd have to do that in all 4 places. Essentially, any data associated with the book is just that. It's an attribute of the book. I can't really interrelate different items easily. For example, Richard Bachman is an alias of Stephen King's. Or detecting it has 1 author but 2 publishers. It's messy. To detect any of these things, you'd have to write some custom code. You probably know where this is leading. Relational databases to the rescue. They solve all these problems. Next up, I'll show you how. In the previous lesson, I covered flat file storage. In this lesson, I'll introduce you to databases and SQL. A relational database gets its name from the fact that it stores the relationships between things. It does this through treating data as a series of tuples. This is kind of like the row in the CSV file you saw in the last lesson, except a row can contain references to another row or in another table altogether. The relationships are identified through the use of keys. There are 2 main types. Primary keys are a unique identifier for a tuple. These are usually integers and typically are auto-incremented by the database engine so you don't have to think about it. The second kind of key is a foreign key. Foreign in this case meaning from another table. This would be the primary key for another object. A tuple containing a foreign key is indicating a relationship with the tuple for which the value is its primary key. Consider the following example. This is a table with authors. PK is short for primary key. Each row in our table is a tuple of the primary key, first name, and last name. I can add a different table of books. Same idea. Each tuple has a primary key, but this time it also has a foreign key pointing to the author table. It and Dead Zone are by author number 1, The King of Horror, Stephen. A foreign key doesn't have to be to a different table. In fact, it can be to another row in the same table. This new column allows me to indicate that Stephen and Richard are the same person. This isn't actually a very good design, as it means an author can only have 1 alias, but it makes my point about foreign keys being able to be on the same table. In a future lesson, I'll address how you would do this properly. As far as I know, every relational database out there supports some dialect of the structured query language, or SQL to its friends. This language is a little different from what you might be used to in coding. It's what's known as a declarative language. That means you write the final state of what you want and the computer makes it so. You're describing what you want rather than how to get it. There's a core set of concepts to SQL that pretty much get implemented by all databases. And then many databases add to the language features that only work with them. This is what is known in the industry as vendor lock-in. For the most part, I'll be sticking to the generic stuff in this course. The beauty of SQL is you don't have to think about the underlying format. The database engine is responsible for that. You can say, create a table, and the database makes you a table. In this course, I'll be using SQLite as my database engine. This is a small, single-file, self-contained engine which doesn't require a server. According to its website, it is the most used engine in the world, and whether or not you know it, you're probably using it. It gets embedded in applications all the time, and there's a good chance it's on your phone right now. SQLite comes with a command line tool that works like a Python REPL, allowing you to interact directly with your database. I'll be starting with that before moving on to SQLAlchemy in a future lesson. Your operating system may or may not come with SQLite. You can grab either the source code or a binary at the link here if you're planning to follow along and it doesn't come by default in whatever you're using. The command line tool that I mentioned for SQLite is called SQLite 3. When you run it, you give it the name of the file that it will be using as its storage mechanism. Once inside, you get prompted. There are two kinds of things you can do here. You can run dot commands or enter SQL directly. The dot commands are built-in utilities provided by SQLite, whereas the SQL will be the language you use to do things in the database. And there is your first SQL lesson. The comment symbol in SQL is 2 dashes. Let's create a table for our authors. The create command takes 2 arguments, what to create, a table in this case, and what to call it, author. The parenthesis is then used to give the command parameters. When creating a table, the parameters are the columns in the table. My first column is the primary key, which I'm calling author ID. It is an integer which can't be empty, and as I said, it's the primary key. The second column is the author's first name. There are several ways of storing text in a database. Remember when I mentioned SQL dialects? Well, here's your first gotcha. SQLite doesn't care about string length. No matter what kind of text declaration you use or how much space you specify, you'll get the same underlying thing. On other database systems, you may have to specify how big this field is. Here, I'm being lazy, knowing that it's SQLite and it doesn't care. The third column is the last name, and then a closing parenthesis and a semicolon to say that I'm done. The table has been created. Doesn't tell you so, but you can ask. .tables is a SQLite command that lists the tables in the database. So far, I've only created one. There it is, named author. With a table in place, let's do something with it. Select is probably the most used SQL command, and its purpose is to select some data out of some tables. The star here indicates that I want all of the columns from the table, and everything to the right of the from is what table to look for data in. Why didn't it do anything? Well, there's no data in the author table, so there's nothing to select. Let's fix that. Insert puts data into a table. Here, I've inserted into the author table. The contents of the first parentheses are the columns in the author table being populated. I'm specifying all of them, not counting the primary key, which is automatic. But if your table has a column that allows empty values or has a default, you don't necessarily have to specify it. The content to the right of the values keyword matches the tuples specifying the column names. So Isaac is the first name and Asimov the last name. No response from this SQL statement. That's good. It means it works. Let me just insert one more. And now I've got 2 authors. I'll rerun the select. And there's the results. The pipe character here separates the columns in the answer. Isaac has primary key 1, while Pearl has primary key 2. The data doesn't usually line up like this. It's just a coincidence that Isaac and Pearl have the same number of letters. Let's insert someone else. And selecting again. See what I mean about the data not lining up? Oh, oops, it isn't Tim, it's Tom. Let's do something about that. The update statement allows you to change a row. The set part says what fields to change, while the where clause indicates those rows that should be changed. I'm being very specific here by using a primary key in the query. An update can apply to multiple rows by having a more generic where clause. I could do something like where author ID is greater than 1, and then both Pearl and Tim would become Tom. And the update worked. Tom it is. Let's try something more specific than select star. That's all the first names. This gives you a fair amount of flexibility. The output doesn't have to be in the same order as the table columns. Let me put Tim back in there. There he is. And now I'll fix it. The delete statement allows you to remove some data. Like with the update, the where clause specifies what rows are acted upon, which means both Tom and Tim are gone. Authors alone are boring. Let's add some books. Up until now, I've been sticking to the SQL convention of using all caps. SQL doesn't actually care. I'm lazy and a Python developer, so I probably won't keep doing that. The colorization here is a feature of the tool I'm using to record this, not part of SQLite, so you might want to stick with capitals to make it easier to read. The highlighting here helps identify the keywords without having to get a cramp from holding the Shift key. Using .tables shows that I now have both author and book tables. Note the foreign key in the book table specified by using the references keyword. Author ID integer references author says that the book table contains a foreign key to the table author. Now I'll add a book. And there it is. The first one is the primary key of the book. The second one is the foreign key to the author. I had to set it to Asimov's primary key. This establishes the relationship between this book row and the Asimov row in the author table. This would be the relational part of the relational database. I'll add another book. And there they are. Now let's do something fancier. I'll be selecting from multiple tables. This is called a join. When you select multiple tables, you can alias the table. This line uses A as an alias for the author table. You'll see in a second where that gets declared. The double pipe symbol is a text join, so the first column of the results of the select will be the author's first name, then a space, then the author's last name. The as statement here creates a name for this column. I'm still choosing what to output at this point. This is the second column, which will be the title of the book. Now I'm telling Select where to get the A info. That's the author table. And to join that with the book table, known as B in the query. The ON clause specifies how to correlate the data between the tables participating in the join. In this case, I'm saying to find all the books and match their author IDs with all the authors. The end result is some data in tabular format with the author's name in the first column and their book in the second column. Think back to the CSV file in the previous lesson. Ignoring the publisher part, you now have enough knowledge to create a select statement with a join that could produce the data you found in the CSV. That's enough for now. To leave the SQLite command line tool, you can press Ctrl-D. You've had a whirlwind intro to SQL. Next up, I'll add some Python to your Python course and use SQLAlchemy to do some SQL in your Python code.